Welcome to video number 5. So this video we are looking at, I've called it stationary points, but the topic is calculus really we're looking at, and I've broken it down into two different parts. So this topic itself, it has stationary points, so dealing with stationary points, finding its nature, and then it also has minimum and maximum application questions, which are usually seen as quite a tough topic. So the first few things I wanted to recap with you are just knowing the definitions of what's happening in terms of the calculus at certain definitions. So knowing that stationary points are found where our first derivative is solved equal to 0. Now, something that's handy to know about this topic is why things happen. Okay, so why is it called a stationary point? What's happening there? And the reason it's called a stationary point is because it's where the particle, if it's moving, it becomes stationary because it's about to turn back around, okay? Or something's happening at that point. So it's stationary at that point, okay? So that's the idea, why. And it's where our first derivative is equal to 0. That's because our first derivative is talking about gradient. And the gradient is 0 at that turning point, okay? All right. Then when we get into the nature of these stationary points, we have minimums where our second derivative is greater than 0. And I think, okay, well, it's where the second derivative is positive. Positive, if you're positive, you are smiling, and that gives you the minimum. If you're below 0, you're negative. If you're being negative, you have a sad face, okay? And then knowing that a point of inflection is where our concavity is 0, okay? Now, horizontal point of inflection is where both, at that one single point, our second and our first derivative is equal to 0. So it has 0 concavity and it has 0 gradient. So one part of the HSC that's been tested quite a lot, I think I've noticed that since 2012 when they started multiple choice, they nearly put one of these in every multiple choice question. And it's something to do with a graph, and they'll put certain points on it. So they might have A, B, C, and D listed in some form like that. They'll just be random, well, not necessarily random, but points on some curve. And I've roughly drawn a curve here. It's not a great curve, and they're just testing you about you knowing what's happening there in terms of the gradient and the concavity. So let's think about our gradient to start with. Let's look at A. At the point A, our gradient is 0, okay? It's flat. So at that point, my first derivative is equal to 0. My second derivative, so my concavity, at that point is a sad face, so maximum. So my second derivative is less than 0. Okay, first derivative here, I have a negative gradient. I'm going downhill. So f dash of x is less than 0. My concavity at this point, though, is where the concavity is changing. So notice how it's gone from being a sad face to a smiley face. So this is where my second derivative is equal to 0. Now, this is quite a rough drawing I've done here, but I've tried to make this what we call the horizontal point of inflection. That's where I've gone flat for a second. Oops. So my first derivative is 0. And at that same point, my concavity is changing. So both my second and my first derivative is 0, which is the definition of a horizontal point of inflection. Now, the last one I've just thrown in there really is a trick. People think, oh, is something to do with the intercept happening here? Does that affect anything? The answer is no. So at this point, I'm going uphill. So my first derivative is going to be greater than 0. And I'm part of a smiley face, which means my second derivative is also positive, greater than 0. So being able to pick random points on some big curve and know what's happening in my first and my second derivative, that's an important skill. And you'll notice that came up in these 3 past HSC questions. So let's have a look at them to start with. hopefully now this becomes a lot easier for you, okay, now that you've seen the example I just did. So we have the diagram shows the graph, and which of the following statements is true at that point A? So at this point here, we want to talk about what's happening. Straight away, once I said, like I just said, if you just did that activity and you understood it with me, this will be a breeze now. Let's think my first derivative is my gradient, and that's definitely uphill. So straight away, I have a first derivative that's uphill, so it's greater than 0, which is going to knock out C and D, where they're both less than 0, okay? So then it just leaves me with my concavity. At this point here, I'm concave down, which means I'm sad-faced because my second derivative is less than 0, it's negative, which leaves me with A. Easy. And they love putting these in multiple choice. So next we have an interval here, and we need to pick which graph best represents f of x, and f of x should have a first derivative that's bigger than 0 and a second derivative smaller than 0. So straight away, the first thing I'm going to think, okay, first derivative bigger than 0, I'm going uphill because my gradient is positive, which means this one is out because it's downhill and downhill. So from left to right, both of these are going uphill. Second thing then is my concavity. My concavity is less than 0, which is a sad face, okay? So the only one then that's left is going to be also A. And finally, this one should look familiar because it's very similar to the one I just did. So pause the video if you want and give this a go. You want to know where the first derivative is positive, so we're going uphill, and my second derivative is equal to 0. So straight away, I think, well, positive gradient's got to be going uphill. So that's A's out. B could be it, C's out because it's flat there, and D could be it. Now I think about my second derivative. My concavity is equal to 0, which means it is a point of inflection. Where is my concavity changing? D has no concavity change. It's a minimum that whole way. But B definitely does. It's sad face here, smiley face here. So the answer is B. Hopefully that clears things up for you. It's a great summary to make on what we just did in this page above. And pick your own curve if you want, and then do it as an exercise. Just remember, first derivative is gradient, second derivative concavity. Alright, let's have a look now at how we can apply all this knowledge in our calculus to style question. So we have start with a graph, f of x there. First question, find the values for which of x for which the first derivative is equal to 0. So I need to differentiate and solve it equal to 0. And there I have it, my first derivative, and I solve it equal to 0. I get the x values of 0 and negative 2 give me my first derivative to be equal to 0. Now it says find the values of x for which it is less than 0. There are a few ways to do this. So we've got a quadratic because it's power of 2 and an inequality. Quadratic inequality, test a point, okay? That's one of those things that you just need to be able to recognize. Any quadratic inequality, you're going to have to test a point. What I'm going to do though is I'm going to come back to that because I want to show you another way that that can be done with the graph. So let's go to part 3, coordinates of the stationary points. So remember, stationary points. We differentiate, we solve it to equal 0. That gives our x values of our stationary points. We then find the y value of our stationary points and determine their nature. So what we actually have here, in fact, these are the x values of our stationary points. So now I just need to know what are my corresponding y values at these x values. So sub your x values in. So I found my corresponding y values. So therefore my stationary points are 0, 2 and negative 2, 6. Okay. Alright, so I found my stationary points. Now it says values of x, so we need to find values of x for which the curve is concave down, okay? Then we have to find the points of inflections and then sketch. So I'm going to next determine the nature. I determine the nature of stationary points by taking my second derivative, subbing in the x values into that, and that's when I say are they positive or negative. So here I go. And there we have it. So I took my second derivative. When I differentiate again, I get 6x plus 6. I'm subbing in then the x values of my stationary points. Okay. Now, I got a positive number when I subbed in 0 into my second derivative. I got 6, which is greater than 0, which is a smiley face, so therefore a minimum. When I subbed in negative 2 into my second derivative, I got negative 6, which is less than 0, sad face, maximum. And I write that therefore statement, okay? Now, I'm also going to come back to this question. In a HSC, both of these questions, actually, part 2 and part 4 are always asked after you draw the graph, and I will show you why, okay? So technically this question I find is in a bit of a strange order. They can be done obviously without the graph, but it's a lot more helpful to see the graph and then find those values. So I need to now find the coordinates of the point of inflection. Think about what's happening at a point of inflection. At a point of inflection, my second derivative is equal to 0. So I just solve my second derivative equal to 0. So my second derivative was 6x plus 6, and put that equal to 0. You'll find when you rearrange that, you get an x value of negative 1. Once again, it does say find the coordinates of the point. So once again, subbing in negative 1 into my original, and you will get negative 1, 4. Okay, so therefore, I have a point of inflection at negative 1, 4. All right, I'm going to now sketch my graph. Okay, so I start with labeling everything I know on it. Okay, I know that there is a stationary point at 0, 2, and it's a maximum. So I put a little sad face on it. And I know at negative 2, oh sorry, that one's the minimum, isn't it? So I put my smiley face on. And at negative 2, 6, I have my maximum. Always label them. And now join them. There we have it. Okay. Now, in this course, you aren't expected to be able to factorize something like that, so you don't have to have your x-intercept there. Okay. If you could factorize that and solve it, you definitely would put your x-intercept. Well, I would anyway. All right, so I've sketched my graph. Now let's go back to those questions I skipped. I'll show you how we can now look at the graph and do them, which is the way the HSC is usually set out so that you can do them straight off the graph. So straight away, part 2 said find the values of x for which your first derivative is less than 0. First derivative less than 0. That's my gradient is negative. So let's look on this graph when my gradient is negative. The only place that this is going downhill is right here. So my gradient is negative for all of the values of x that are between negative 2 and 0. Now it's only in between them, not equal to them, because at those points my gradient is in fact 0. So it's just all of the points in between. See how easy that is looking at the graph. All right, and so that was the answer to part 2. Part 5, part 4. Find the values of x for which the curve is concave up. So let's think about concave up. So that is your smiley face. Yes, my smiley face. So let's think my smiley face is from here down and up that way. One thing I didn't do, which I definitely should have, is labeled my point of inflection here. All right, now notice how I stopped here. That's because after that point, from here onwards, that's where it goes sad face. Okay, so I'm just looking at where it's a smiley face. And from finding that point of inflection already, I know that it's all the x values that are bigger than -1. Again, not equal to -1 because at that point, my second derivative is 0. Okay, so it's not concave up nor concave down. So notice how much easier that is with the graph there. And I've only ever seen HSC questions ask you to do those after they get you to sketch it. Alright, pause the video if you like and give this one a go. It is slightly harder. It just says determine the nature of the stationary point at x equals 0. So it's in fact not asking you to do everything else. It just wants to know what is the nature of the stationary point at x equals 0. Otherwise, if you're not pausing or if you have already paused, let's have a look at it. It gives us the derivative, okay? So straight away we have our derivative. Determine the nature of the stationary point at x equals 0. So once I usually have differentiated, I would solve that equal to 0 to find my stationary points. Now I know that they only want the one that at x equals 0. They want its nature, which means straight away I'm going to have to differentiate again to determine its nature. So differentiating this, I'm definitely going to expand it all and then differentiate. So when I'm expanding, I'll forget the x squared to start with and just FOIL out my two brackets and then multiply that in. Alright, so I expanded and I said, okay, my derivative can also be then written in the form 2x to the power 4 minus 3x cubed plus x squared. So now I can differentiate that, come down, and I get this value. So remember, we want to know the nature of the stationary point at x equals 0. So now I'm just going to sub my x value in to my second derivative to find its nature. And I get 0. So this is why I've put this question in here, because of this very situation we're in now. What happens if when I go to determine my nature, I don't get a negative number, I don't get a positive number, but I get 0? The first thing you're going to do is say, all right, that's a possible point of inflection. Okay, it's a possible point of inflection. We need to find out if it is for sure. Okay, and you always must check before you say it is a point of inflection. So what we have to do, the x value of the stationary point that we have found a possible point of inflection for goes in the middle here. Whatever the x value is, it may not always be 0. In fact, it's not always 0. It's whatever the x value of the stationary point is, you put here. Now, we then put x and our second derivative in here. Some people do first derivative here, I do second. Then I put a number in here just on the other side of 0 and on either side of it, okay? Now this number we're going to use, it needs to be only just on the other side because we don't want to go too far away from this stationary point when we're testing. So all you're going to do is sub in negative 0.1 and 0.1. And I'm going to sub them into my second derivative. When I sub them into my second derivative, whatever this, it doesn't matter what number I get, it's just the sign, okay, whether it's positive or negative. I know that when I sub 0 into my second derivative, like I just did here in blue, I get 0. So I know that already. It's just whether it's a positive or a negative number. So sub it in to your calculator and see what you get. Okay, if I have done that correctly using just my phone calculator, which is a bit dodgy, you get a negative number, a 0, obviously, then a positive number, subbing it in. Now, that means my concavity changes on either side of that point of inflection, or possible point of inflection, which means if my concavity changes, it's gone from a sad face to 0 to a smiley face. So therefore it is a point of inflection. So that's what your answer would be, okay? Now, there's one last thing though. Any time you have concavity changes, so therefore point of inflection, and that's something I would write. Since my concavity change 0, 0 is a point of inflection, I must always check for horizontal point of inflection, okay? Any time you get yes, it is a point of inflection, you have to check and see if it's also horizontal. So remember the definition of a horizontal point of inflection. It has my first and my second derivative equal to 0 at that point. So I know my second derivative equals 0 at that point. That's what we just did. I have to see if my first derivative equals 0 at that point. That's just a matter of doing dy on dx and subbing in x equals 0, because that's my x value of my stationary point. And when you sub that in, you're going to get 0. So therefore, since my first and second derivative equals 0 at that point x equals 0, it is a horizontal point of inflection. So note to self, if you get a point of inflection, always test to see if it's horizontal. Okay, so part 2 is now moving on to our minimum and maximum application questions. Once again, these are tough questions, but they're always in the HSC and they're worth quite a chunk of marks. Part 1 is always, well, usually a show question, and part 2 is then when you do the application of calculus part, and it's about the minimum and maximum. So what I have here is a little summary of what you do, and you do this every time. So for the show part, which is often actually the hardest part for most people, to show it can be written as some sort of formula, my best tip for you after doing many types of these questions, it's about start with 2 formulas. Then it's just a matter of sub one of the formulas into the other. And sometimes that step may vary, but a lot of the time that's all you're doing. So you just need 2 formulas, and they'll give you the hints on those 2 formulas. With the minimum maximum part of the question, it's just about differentiating whatever you just showed. Then solve it equal to 0, just like you would for stationary point style minimum maximums. Differentiate, solve it equal to 0, then you're going to differentiate again and sub it in and show that it's a minimum or show that it's a maximum. Okay, so let's have a look. We have a can of baked beans is in the shape of a cylinder. We have to, given that the volume of the can, so the volume of the cylinder, can be written as 500 centimeters cubed, we need to find an expression for h in terms of r. So part 1 is not the show part, it's not the application part. They just want you to find an expression for h in terms of r, which means we want h equals something with r in it. That's what that means. So straight away, I'm going to think about the fact that they said the volume is equal to 500. So what is the volume of a cylinder? It's the area times by the height, which is going to be pi r squared h. So therefore 500 is equal to pi r squared h. And they want h equals in terms of r. So I'm just going to take my pi r squared over and divide it. So I'll then have h is equal to 500 over pi r squared. And that's it. So now part 2 is the show part. Part 2 now says, show the surface area can be written as that. So my first formula I already have now, okay, I just did in part 1. My second formula now wants me to use the surface area. So I think I know the surface area of a cylinder. Again, you should know these off the top of your head. 2 pi r squared plus 2 pi r h. Now notice what's different about their formula. They have the 2 pi r squared, but the 2 pi r h is gone, okay? In other words, there's no h, it's all in terms of r. Which means I just take this and I sub it down in here for h. So this is that substitution line. So when I get that, I'm just going to clean things up. And that's what I end up with. My pi and r will cancel, and 2 times 500 gives me 1,000. So there's my proof done. Alright, now is the last part. If the area of the metal used to make the can is to be minimized, so minimum, find the radius. So we need to find the radius such that it makes a minimum. So we need to, once again, what are my steps? I differentiate, I solve to equal r, and I check that gives me a minimum by differentiating again. So let's start by differentiating this. Now, the first thing I'm going to do by looking at that's not pretty. So I'm just going to remind myself that that's the same thing as writing it as r to the power of -1. And now I differentiate. Remember, I'm differentiating in terms of r, which gives me that, which I can rewrite back in the form, taking my r squared back underneath. Now I've differentiated, my second step is to solve that equal to 0. So if I'm solving this equal to 0, I'm just going to take that negative fraction to the other side. Times my r squared over. Then divide and cube root. So there's my value of my radius. I need to now check that is going to give me a minimum. So to do that, I need to differentiate again. I'm going to do this in a separate color. And note, when I differentiate, I'm going to go from this line here with my negative indices, so s double dash. So this time I'm going to just be left with 4 pi positive 1000 over r cubed. So I'm just jumping ahead there. Now I have to sub this is like my x value of my stationary point, remember? To determine its nature, we sub it into our second derivative, and it's just about whether it's positive or negative. We want to show it's a minimum, so we want to show this is going to give me a positive number. So let's have a look. If I sub in, I'm going to get 4 pi plus 1000 over the cube root and the cube, we're going to cancel each other, which is just 250 on pi. Okay, and cleaning all that up, I don't even have to show too much more. I can just say, therefore, it's going to be greater than 0. Therefore, smiley face. Therefore, minimum. And to finish off that question, I'm just going to say something along the lines of, therefore, the radius of the cube root of 250 on pi will give the minimum amount of metal needed. So hopefully that helps. They are tough questions. That one wasn't too bad. But have a go at some past paper questions now. Just remember, you're going to start with 2 formulas, sub one into the other, and then the minimum maximum part, that's just where we just do what we normally have done and differentiate, solve it equal to 0.